Hello viewers, today we are going to discuss two special methods of finding the derivatives of implicit functions and also the inverse trigonometric functions. What exactly do we mean by implicit functions? So far we have been using functions of the form y equal to f of x, where we had y is equal to sine square 2x plus 1, or y equal to x cube plus 2x minus 1, or y is equal to under root 1 minus cos x by 1 plus cos x, and you could find their derivatives with the appropriate rule applied. Such functions where y is clearly expressed as a function of x are called the explicit functions of x. What happens in these cases? Can you solve y in terms of x? Can you express y as a function clearly written in terms of x? Perhaps as you look at each one of them, you will be able to say no. Such functions where there is a dependence of y on x, but y cannot be expressed explicitly in terms of x, we say that y is an implicit function of x. And today we are here to discuss the differentiation of implicit functions. How do I find dy by dx if I have an implicit function? In this case, the relation is sine square x plus cos square y is equal to 1. So, task is the same. I have to find the rate of change, that is the instantaneous rate of change of y with respect to x, but I cannot express y in language of x directly. What do we do? Let us demonstrate. Differentiate the relation with respect to x, we get derivative of sine square x plus derivative of cos square y equal to derivative of 1. So, we are differentiating both sides of the given expression. Derivative of sine square x is not a problem, but note that cos square of y is present, not x. So, this is where you have to watch out. Using the chain rule, I get the derivative of sine square x as 2 sin x cos x. We are interested now in understanding what would be the derivative of cos square y would be. Again, it is a composition. Outermost function is the square function, then cosine function, and then another function, that is y, which is a function of x present. Therefore, applying the chain rule, I get the derivative as 2 cos of y into the derivative of cos of y, and the right hand side of course is 0, because derivative of a constant is always 0. Further, this becomes same as 2 sin x cos x as it was plus 2 cos y, and now the derivative of cos y using chain rule is minus sine of y into the derivative of y with respect to x. From here, we will just now separate out what dy by dx is. Rearranging, you get dy by dx as sin x cos x upon sin y into cos y. So, chain rule actually plays a significant role in finding the derivatives of implicit functions. Let us consider one more problem and see if there are other things that you need to be careful with. We have the question which says find dy by dx if sine of x y, the product x y plus x by y is equal to x square minus y. Again, differentiating the relationship with respect to x, we get derivative of sine of x y plus derivative of x by y is equal to derivative of x square minus y. The first term, that is sine f x into y, gives us cos xy into derivative of xy, chain rule again, plus what happened here? What I have used is what you see, I read it as x by y. So, there is a clear presence of quotient rule. Right hand side is just 2x minus dy by dx. Work is still not over because I still have to finish the first term. Again applying the derivative of xy with the help of product rule, I get cos of xy into y plus x dy by dx. The other terms remain the same. Our job was to find dy by dx. So, what you really need to do is to rearrange, rewrite this expression and separate out dy by dx, which will give rise to the final answer written here for you. I will leave the little bit of simplification in between for you to follow up with. So, we have the derivative of implicit functions evaluated using the chain rule. Wherever product and quotient rule present, they play a role. Let us continue with understanding how this and other facts that we have learned so far help us to find the derivatives of inverse trigonometric functions. Since we have a limitation of time, I am not going to discuss the proofs of these results, but these results are going to play a very important role in this discussion, and that is nothing but list of these results or formulas, as you may call them, which suggests that the derivative of sin inverse x is 1 by root 1 minus x square, and yes, there is a condition present on x for this derivative to be well defined. So, those branches, the conditions on x are stated along with. You definitely need to memorize these results, there are no alternatives for it, but the best would be if you sit and work out the proof using implicit differentiation only. Start with y equal to sin inverse x and see what x is, and then work out the proof from there. We will focus on the applications. So, if I have to find the derivative of y, where y is cos inverse of root x with respect to x, what would one do? Again observe composition, 3 layers, no rather 2 layers. I have inverse, cos inverse and the square root function present here. Let us see what would happen if I have to find its derivative using chain rule. Do you think I can write directly as minus 1 by root 1 minus x into derivative of root x? What happened in between? Derivative of cos inverse root x with respect to root x by the formula would be minus 1 by root of 1 minus root x whole square. Isn't that so? That simplifies to be minus 1 by under root 1 minus x. And what is the derivative of root x? Nothing but 1 by 2 root x. That gives you the derivative of y with respect to x as minus 1 by 2 root x into root of 1 minus x. Let us take another question. Find dy by dx if y is equal to cot inverse of root 1 plus sin x plus root 1 minus sin x by root of 1 plus sin x minus root of 1 minus sin x, where x is between 0 and pi by 2. Now, one of the things that you must possibly realize as we go through this statement is that this is a very familiar function. Where did you see that? Remember, we worked on these functions in inverse trigonometric functions chapter and learned how to simplify them, how to write them in their simplest form, and in fact that is what is going to take away the major part of our problem. Derivative would only be calculated once this function is simplified. Let us get down to doing that. Start with y, which is cot inverse root 1 plus sin x plus root 1 minus sin x. upon root 1 plus sin x minus root of 1 minus sin x. What can we do? I can write that sin x as cos pi by 2 minus x all across. Why would one do that? Simply because 1 plus cos theta is 2 cos squared theta by 2 and 1 minus cos theta is 2 sin squared theta by 2. Therefore, 1 plus cos pi by 2 minus x simplifies to 2 cos square pi by 4 minus x by 2 and 1 minus cos x simplifies to be 2 sin square pi by 4 minus x by 2. What is this going to be same as? This is same as writing cot inverse of absolute value of cos pi by 4 minus x by 2 plus sin pi by 4 minus x by 2 and in the denominator the same expression with a negative sign in between. Now, why do we have modulus here? Because square root of a square depends on what a is. Is it going to be positive a or negative a? Depends on a in sense, if a is a positive quantity, then root of a square is going to be a. If a is negative, then root of a square is negative a. So, what do we know about cos pi by 4 minus x by 2 and sin pi by 4 minus x by 2? Are they positive or negative quantities? Remember, there was a condition on x. X is strictly between 0 and pi by 2. So, x by 2 is strictly between 0 and pi by 4. Do you think then we can say that cos and sin of pi by 4 minus x by 2 are both positive quantities, and therefore, y simplifies to be cos pi by 4 minus x by 2 plus sin pi by 4 minus x by 2 divided by cos pi by 4 minus x by 2 minus sin pi by 4 minus x by 2. Now, this is an expression which we have worked with a number of times and know that this can be rewritten as cot inverse 1 plus tan pi by 4 minus x by 2 upon 1 minus tan pi by 4 minus x by 2. In case you have forgotten, what we do is divide numerator and denominator by cos pi by 4 minus x by 2. This leads us to nothing but cot inverse of tan of pi by 4 plus pi by 4 minus x by 2, a very familiar expression. This results in nothing but cot inverse of tan of pi by 2 minus x by 2 leads to cot of x by 2. And see, our y is just nothing but x by 2. So, the derivative of y with respect to x is simply half. So, the task was to find the derivative, and that took not just more than maybe a second to do, but without the simplification it would not have been so convenient to find the derivative. In fact, it is mandatory that you first simplify the expression and then find the derivative. And so, in order to differentiate inverse trigonometric functions, you must perfect the inverse trigonometric functions chapter, and specifically the part where we discuss how to simplify a given expression before you start with the derivatives. Best of luck, work hard, and I will see you next time.